Hi, I'm Dave Lyons. I'm presenting RazUllah in my paper entitled Seeing Red, Hacking Anaglyph 3D to Manipulate Visual Perception. Seeing Red extends our exploration of color perception in print. Using the red-blue colors of the stereoscopic Anaglyph 3D effect, Seeing Red investigates an approach that deconstructs and repurposes the functionality of this effect. The procedures and techniques are hijacked to communicate fundamentally different messages within the same image. This investigation was inspired by our previous success in controlling perceptual experiences between audiences of varying visual acuities, sometimes called colorblindness. Communication of the experiences between targeted audiences was enabled using augmented reality software on digital devices. The current work seeks to establish a similar effect for a broader audience without reliance on high-tech mediation. The core principle of Anaglyph 3D is that two slightly different overlapped 2D images, one shifted red and one shifted blue, create a 3D simulation when viewed with filtered glasses. In Seeing Red, right and left eyes are individually targeted to create separate visual experiences by using color palettes that can be effectively filtered by Anaglyph 3D glasses. Within the overall composition, hidden images are revealed to the viewer when they close their left or right eye. The concept of intentionally providing slightly different images to each eye, which the brain would combine to mimic depth perception, were explored simultaneously in the early 1830s by rival scientists and inventors Charles Wheatstone and David Brewster. Their inventions are called stereoscopes. Because photography was still in development, both early stereoscopes relied on pairs of drawings. Many of the drawing pairs were of similar forms or objects rendered from two different angles to simulate the slightly different views from right and left eyes. These two images, whether they are drawings or photographs, are called stereo pairs. Using a stereoscope, the simultaneous viewing of the stereo pairs result in the visual perception of a three-dimensional object. We know that viewing slightly different images, when directed to different eyes, can create a 3D effect. When the stereo pairs of a stereoscope are combined into a single image, it's called an Anaglyph 3D. One image is printed in red, the other is printed in cyan. The printed images may look somewhat off-register. For the 3D effect, a pair of glasses with one red lens and one cyan is worn. The red lens filters out the red images, so the eye with the red lens sees the cyan image. The cyan lens filters out the cyan image, and the eye with the cyan lens sees the red image. The visual information from each eye is combined in the visual cortex of our brain to form a 3D image. The red and cyan filters used in Anaglyph 3D were chosen because of their relationship to how our eyes perceive color. Human eyes perceive color through three types of light receptors on the retina called cones. The three types of cones are distinguished by the wavelength of light that they respond optimally to. There are long wavelength, mid wavelength, and short wavelength cones, primarily detecting red, greens, and blues, respectively. When all three types of cones are functioning correctly, we perceive the full spectrum of colors. Red and cyan filters are used to approximate a full color image. Red targets red, cyan, being a combination of blue and green, target those two colors. While not a perfect parallel to our three cones, it is effective. Repurposing Anaglyph 3D. From our previous work on colorblindness and visual perception, we know that if one of the three types of cones do not function, that person's perception of certain colors is different than someone with fully functioning cones. With this knowledge, we were able to group colors together so that the visual experiences would be radically different, but intentionally designed dependent on one's visual abilities. Initial experiments were done manipulating images to create different experiences for viewing through right and left eyes. Images were created where fingers moved and eyes blinked. Artists know that visually, most people tend to group warm colors, reds and magentas, and cool colors, blues and greens, separately. Thus, contrast can be created using cool colors and warm colors. Those with fairly common red-green color blindness exhibit different color grouping preferences. They tend to group what others considered red and green colors together because to them they all appear as muddy yellows. Similarly, blue and magentas are grouped together because they all appear blue. Color contrasts for these audiences are most easily made using blues and yellows. So for the typically sighted, red and magenta are a pair of warm colors. The contrasting cool colors are green and blue. For those with red and green color blindness, blue and magenta are similar colors, with both appearing blue. Colors that are visually contrasting to them are red and green, which both appear as yellow-browns. Using this knowledge of different color perceptions by these two different groups, we were able to group the colors strategically, allowing for the creation of visual messages to one audience, which were camouflaged to the other. While red-green color blindness is caused by non-functioning red or green cones in both eyes, the Anaglyph effect is created by targeting either red cones in one eye and blue and green cones in the other, thus creating an artificial parallel to color blindness, although different for each eye. Because of that similarity, it was hypothesized that we could create a similar way of grouping colors using Anaglyph glasses. To understand how colors shift when filtered red or cyan and how to group them effectively, we started with a spectrum of 10 colors: red, medium violet, dark purple, light blue, dark blue, gray blue, blue-green, green, yellow, and orange. A 2x5 square grid pattern was created in Adobe Illustrator. Each one of the 10 squares was assigned one of the 10 colors. To be able to do a side-by-side evaluation of the anticipated color shifts viewed through the lenses of the Anaglyph glasses, a simulation of the color shifts was created in Illustrator. The resulting colors did not match what was observed when looking through the Anaglyph glasses. The idea of doing analysis of the colors on the computer screen was abandoned. Instead, each of the 10 colors was viewed on its own and then with an eye looking through the red lens of the glasses. Illustrator Color Picker was used to identify the red shifted colors in each case to generate a new palette of 10 red shifted colors. The same process was applied to the original 10 colors using the cyan lens of the Anaglyph glasses to generate a second new palette of the 10 cyan shifted colors. In most cases, the baseline colors had to be adjusted to maximize the visual impact of all three sets of colors. This was an iterative process. The expanded refined colors and the colors they shifted to when observed through the red and cyan lenses of the Anaglyph glasses are described in Table 1. With this information, we can break colors down into groups that look like reds when filtered with the red lens and those that look like blue when filtered with the cyan lens. Additionally, we can identify the colors that are neither red nor blue when filtered. This is documented in Table 2. This exercise demonstrated that, for the most part, whether filtered red or cyan, reds remain red and blues remain blue. Helpfully, violet looks red when filtered red and blue when filtered cyan. Orange shifts red when filtered red, green shifts blue when filtered red. Gray shifts blue when filtered red or cyan. White shifts red when filtered red, but remains white when filtered cyan. To create images to be viewed through the red lens, We contrasted colors that appeared red and blue when filtered red. The red colors are pink, red, yellow, orange, and white. The contrasting blue colors are green, light blue, medium blue, dark blue, and gray. Images to be viewed by the cyan lens would also contrast red and blue colors when filtered cyan. The red colors are pink and red. Where red and blue imagery overlapped, violet was used because it shifts both red and blue. Moving from RGB monitor colors to CMYK print colors caused colors to shift. The effect some colors had when viewed on the monitors would not reproduce once digitally printed. Adjustments and compromises were required. Compounding the gamut issues was ambient light and the differences between brands of Anaglyph glasses. Through careful observation and adjustments, colors were fine-tuned to be optimal for prints viewed in daylight with minimal effect caused by variation in glass quality. The final color set documented above reflects those adjustments. Initial tests. The first test that grouped colors into perceived reds and perceived blue was a grid made of 32 by 32 squares. Repeated medium blue and violet squares made up rows that alternated with rows of repeated green and red squares. The intent was to create a gingham pattern, which when filtered red would appear as a series of vertical stripes, and when filtered cyan, the composition would look like horizontal stripes. The test gave the anticipated results. Having established that simple conflicting messages could be communicated to each eye, more complicated hidden imagery was attempted. A composition of 9 squares laid out 3 by 3 was created. Each square contained related compositions testing combinations of contrasting colors. Each, when viewed through the red filter, the cyan filter, and unfiltered, appeared strikingly different. Conclusion. The initial experiments have promising results. Both image and color experiments reveal imagery can be created that not only targets individual eyes with Anaglyph glasses, but when viewed unfiltered through both eyes, create cohesive images. The variety of colors explored here was limited. A greater range of hues, shades, tints, and tones may reveal enhanced effects. If similarly created imagery is to be viewed on its own, cyclical environmental lighting, full spectrum, tinted red, tinted cyan, may be a substitute for the Anaglyph glasses. Finally, appropriate imagery, which moves from proof of concept layouts into multi-layered expressive images, will be best placed to utilize these results.